Let's talk about a really clever engineering trick that can make training these incredibly powerful AIs up to 60% faster. It's a huge deal, and it all boils down to fixing one single critical bottleneck.
So here's the big question, right? How do you actually build an expert AI that's tailored for your company? And maybe more importantly, how do you do it without it taking weeks and costing an absolute fortune? We're going to dive into exactly how the team at Applied Compute cracked this problem, making reinforcement learning way more practical for the real world.
Okay, so first things first, we need to get a handle on the main tool we're using here, reinforcement learning, or RL for short. The best way to think about it is like you're creating a specialized AI expert completely from scratch, and you're teaching it just through trial and error.
It's kind of like training a digital apprentice. It starts off knowing nothing, but the more it works on your company's specific problems and gets feedback, the smarter and more specialized it becomes.
Here's a great way to picture how this works. Let's say you want to teach an AI to solve a math problem. You have it try the same problem maybe 100 times. Then you grade all 100 of its final answers. Now, for every single time it got the answer right, you go back and reward the specific line of thinking it used to get there. And for every wrong answer, you do the opposite. You discourage that behavior. You do this over and over, thousands of times, and eventually it becomes a real math whiz.
But, and this is a big but, there's a catch. The standard way of doing this, something called Synchronous RL, has this massive bottleneck built into it that just wastes an incredible amount of time and, you guessed it, money.
You see, in this old-school setup, the two main jobs, the sampling, where the AI makes all those attempts, and the training, where it learns from them, they have to happen one after the other, in lockstep. The training part literally cannot begin until every last sample is finished. This means your whole expensive system moves at the speed of its single slowest piece. And this chart just shows you how bad the problem really is. In a real-world test, 99% of the samples were done in about 40 seconds. Pretty good, right? But the entire system had to just sit there and wait for an extra 80 seconds, that's double the time, just for that final 1% to finish up.
And during that long 80-second wait, what are your super expensive, super powerful GPUs doing? Absolutely nothing. They're just sitting there, totally idle. As the team at Applied Compute puts it, the GPUs are slacking, and that is a huge waste of resources.
So how in the world do you fix this? Well, the solution is to completely break that rigid step-by-step process. You use a method called Asynchronous Pipeline RL, and you build a much, much smarter system. So instead of having one team of GPUs do both jobs one after another, you create two specialized teams that work at the same time. One team does nothing but generate samples, constantly, and it just dumps them into a queue. The other team does nothing but pull samples from that queue and train on them, constantly. They're working in parallel, which means no more wait. But, there's no such thing as a free lunch. This awesome new speed introduces a brand new, kind of tricky problem. It's a classic engineering trade-off, and it has a name: staleness. So here's what's happening. Because the training GPUs are updating the AI model all the time, the sampling GPUs might be halfway through generating a sample when they get new instructions from an updated model. This means that a single sample might have been created by a few different versions of the AI. It's like trying to study from a textbook that someone is editing while you're reading it. The information is a bit out of date or stale. And this brings us to the crucial trade-off. If you allow for high staleness, your GPUs are always busy, your runs are super fast, which is great. But if the data gets too stale, the AI can get confused and the whole learning process can become unstable and even fail completely. It is a really delicate balancing act.
So how do you find that perfect balance? I mean, you can't just run dozens of these super expensive multi-day experiments to find out. That's just not practical. The answer? You build a highly accurate simulation of the entire system first.
The team basically built a digital twin of their whole pipeline. It was a complete simulation where they could model and tweak the 4 key variables that really define how the system behaves. How many GPUs you have to work with, how big your workload is, and the speed or throughput of both your sampling team and your training team. Now, the whole point of this simulation was to solve one single, all-important puzzle. How do you split your GPUs between the sampling team and the training team? And it had to solve this puzzle while following 2 rules. First, you have to make sure data is being produced just as fast as it's being used up. And second, you have to make sure that staleness number never ever goes above a safety limit you've defined beforehand. And this is where all that deep systems modeling really pays off. The result is pretty incredible, and it leads to a massive, very real performance gain.
By simulating all these different configurations before they even started the real job, they could figure out the absolute perfect split of GPUs for their needs. End result? This new optimized setup was up to 60% faster than the old inefficient synchronous method. That is a massive, massive saving in both time and money.
So what's the big takeaway from all this? Well, it's that putting cutting-edge AI to work in the real world isn't just a machine learning problem. It is a hardcore systems and engineering challenge. It forces you to understand the entire system from the ground up.
And it really makes you think, doesn't it? If we can perfectly model and optimize the system that an AI learns on, what's the next big barrier we need to break down? Maybe the future of AI isn't just about writing better algorithms, but about building much, much smarter systems to run them on. Thanks for watching.